Claude, no shit, it all depends on where you put the comma. So we're going to talk about space. There's a lot of different type of interpretations of space, like emotional space, inner space, this space. But I'm going to talk about like the real old kind of like outer space, okay, old school space. And probably the sideline, the subnote for this talk is probably how the infinitely large is actually determined and constrained by the infinitesimally small. So I was an astrophysicist, but it's complicated. I founded the Department of Astronomy in McGill before I founded a startup, Nexology. And what I do now is a bit related to what I used to do. But one of the things that the reason why we got to publish in Nature and what we did was really groundbreaking is that we tied basically quantum mechanics, which is that crazy like Heisenberg uncertainty principle stuff, with cosmology, which had never been done before. And so I'm not going to just show you nice pictures. Like the initial picture we saw there was great. That's called the Fingers of Creation. It's one of the biggest star nurseries in the world, which was taken by the Hubble telescope, which, conveniently, the talk will be structured in two things: beginning, end. And it'll be structured with two people: Edwin P. Hubble, Big Bang, and Einstein. Okay, and it's almost like a fight. Because Einstein, quantum mechanics, didn't get along. So round one. Edwin P. Hubble in the left corner. Woo! Okay. Whoa! Okay, Edwin P. Hubble. Styling, come on. He could be Monocle magazine, this guy. But like 70 years ago. But also, Edwin P. Hubble was a badass. Okay, he enlisted in the First World War, became a major, boxed all his life, and I know from people who've worked with him, kicked the shit out of his grad students in boxing matches. Oh yeah, you think the universe is expanding slowly? Let's take it in a round. Me and you. Okay, badass, not a nerd. This guy, nerd. So this is Grand Maître, who also was working at the same time as Hubble on different stuff, but didn't publish in this cool papers. Science, a lot of people who are not in science think science is an absolute. That's because basically the teaching of science to arts students basically finishes science with Mary Shelley. And then once we had that was the romantic view of science. But actually, quantum mechanics put everything on its nose, and quantum mechanics is more akin to Taoism. People have heard of the Tao of physics. Have you heard of this? The Dancing Wu Li Masters. Read those books. It'll change your mind about stuff. Okay, so this is more like Professor Snape, not a very cool guy. And sociologically, he was a Belgian priest who proved also that the universe is expanding. But Hubble won out. Hubble got all the credit. And this happens over and over again, like Leibniz and Isaac Newton. Same debate. So what are these guys doing? Fundamentally, they were doing the same thing at the same time in two different parts of the world. And so they're looking at galaxies with, at that time, really good, powerful telescopes. And they're looking at galaxies and they're trying to measure how far away the galaxies are from Mars. And what they found is that when you look at galaxies farther away, the galaxy is actually moving faster away from you. It's like you stink. Okay? Or you're really, really ugly. And as soon as you come to see someone, they go, oh, sorry. This is what's happening in the universe. And this is Edwin Hubble's. This is from the paper 75 years ago. This is the actual data he had. Just to prove to you that this is real, this is with 1,500 other galaxies, and it's a total beautiful linear relationship, which is amazing. It's probably one of the most amazing things about space and time and nature is that it's incredibly complex, it's incredibly huge, and it obeys y equals mx plus b, which is ridiculous how simple that is. So the only kind of situation, unless you really stink, the only kind of situation where when you're in one place and you measure other things around you and the things that are farther away are moving faster is when you're also on a grenade. Okay? Because if you can just imagine here, you're supposed to be creative type, so do this with me, okay? Boom. You are a tile on a grenade. And I pull the pin. What happens? You'll see all the other tiles moving away from you as the grenade explodes. Okay? And as the grenade keeps exploding, you're going to be hanging on to that tile. And what you'll see is that every piece of the grenade that is farther away from you will be moving faster away from you. We are actually, the Big Bang didn't happen. The Big Bang is happening. It's still happening. Okay? So the other way to look at it is a muffin. Okay? Who had pain au raisin this morning? Okay? You actually ate something that before you cooked it, all the raisins were like next to each other and like in a moldy dough, right? And then we cooked it, and what happened? Boom. Space-time. All right? All the raisins are moving away from each other. They're seeing the same thing that you would see if you were on that grenade. And the same thing that we see time and time and time again, and this is like verified even today, when we look at galaxies far away, they're moving faster and faster away from us. Okay? Oh, the balloon. Where's the balloon? You have a guess? Not in the bag. So, well, we'll have to talk for a few more minutes then. I had a balloon with stars on it that was going to blow, and you're going to see the stars expand, but it's all, yeah, I know. Yeah, I'll give you one of the galaxies. This is much better. So literally, right? This was the early universe. It was like, and the early universe was very, I'll talk about the early universe. But before the Big Bang was a TV show, okay? It was like, kind of like the history of the universe is the way we look at the Big Bang. And the Big Bang isn't, people think, so one of the things I used to do in my previous life as an astrophysicist is I helped people design dance. Who knows Au Vertigo? So I was a creative helper for 2 dance shows, Luna, which is about the moon, but literally about expansion of space-time. So I worked with dancers trying to go, okay, well, like the Big Bang, it's not an explosion, so don't do the thing with your body. It's like an explosion. It's more like an expansion. You know, it's like, okay? That's the Big Bang. Okay? So this is actually, if you were all the early universe, it's like everything was close together, and literally, see all the stars? They're all moving away from each other. Okay? I'm not going to make it explode, but what, no. But what made, just as a side note, what made Stephen Hawking famous amongst other things, was that he thought there was going to be a big crunch. Okay? And there is not going to be a big crunch. He was wrong. So, third law of thermodynamics prevailed. And it was a Quebecois person who proved them wrong. So, yay, Montreal. So this is the traditional way of looking at the Big Bang. Roughly, the universe is about 14 to 15 billion years old. And roughly, we know everything, kind of physics will explain everything up to here. And my mom, I'm a Franco-Ontarian. It was illegal to teach French in Ontario. Your choice was be illiterate or become an Anglo. Change your name. And my parents chose to keep the culture. And so they're illiterate. And so my mom goes, what are you doing in school? You're like 27. You should be working somewhere. So I used to explain her what I was to do to my mom, who had a grade 4, grade 7 education. So I had to explain the Big Bang and all this stuff. And my mom was also religious. And she goes, so, Claude, I went down to 10 to the minus 10 seconds. So I was about here, right? And then I explained everything, the 14 billion years. My mom goes like, Claude, there's not very much room for God in there. And I was still like, I was an altar boy till I was 18, right? And so I went, Mom, God has about 10 to the minus 10 seconds at the beginning of the Big Bang. Tons of time for him. So if you ever have to reconcile faith and physics, it's possible. Einstein did it all the time. He was a deeply, deeply, deeply religious person, right? And so and Grand Maître, who was a priest. A lot of religious people, the Tao of physics. Physics by itself is transcendental, okay? There are a lot of ways to transcend, but doing math for 10 consecutive hours without speaking to a human, believe me, your mind goes somewhere. And quantum mechanics, by its very nature, is so screwed up that, well, basically, I wanted to do superconductors until I discovered quantum mechanics, and it was the postdoc of Stephen Hawking who taught me quantum mechanics, and I was like, okay. It was literally like I met Jesus and I walked away. And I'm like, yeah, I'll follow you. And I just did quit. I was doing a double major in philosophy. I dropped philosophy. I did just pure quantum mechanics, and then went, my previous career. So, which took me everywhere. Like I went, built telescopes in Africa. Lived in Paris for 5 years. Kind of like the idea, if you have a passion, and this is why you're doing a startup today, 100% follow your passion, and it'll drive you to destruction, and that's what spirituality is. Destroy yourselves, do it, make it happen, or renew yourself when you're doing it. Physics was that for me, still is. So another way of looking at the Big Bang, though, is probably, so now we're going to flip, right? That's a normal space way of looking at it. But ultimately what's happening here is that they're tiny, tiny, tiny little particles that are determining everything. So most of the matter in the universe, like when I hit this wall, mostly empty space, okay? Trust me, this, empty space. This is where it gets a little Taoish, okay? Because what this is I'm not feeling actually matter, I'm feeling protons who don't want to get closer to each other, pushing back. And so these protons, this is a hydrogen atom, don't want to get closer together. They're like monogamous couples that go, yeah, stay there, we'll have dinner every now and then. It's okay. We'll be our little units, and you guys stay there, I stay there, and that's it. That's what the universe is today. Okay? We're living in an electromagnetically dominated universe. Okay? Where the electromagnetic forces are the big, strong, push everybody around forces. These are the particles, the whole standard model, all of the world, everything that from the Big Bang is understood with something called the standard model. Not very original name, sorry. But we got original when we started naming these things. This is got the up and down quark, the charm and the strange. This is beauty and top, okay? And you can put any connotation you want in those. And these guys kind of like are the people, the building blocks of matter. These people, the bosons, they exchange energy. Okay? That's the roles that they have. And without very much energy, the bosons can't do very much. Okay? So in the early universe, forget about this. There are no galaxies. There are no stars, no planets. There is no matter as we know it. No molecules. So all these things that you've learned, gone. There is no atoms. Shit, there weren't even any protons because protons are made up of quarks. There was no structure. Okay? It was like living in a big fucking pool party all the time. Everybody sliding over everybody else, all mediated by the bosons. Okay? That was the early universe. Okay? Big commune of fun. Okay? And you see the Higgs boson right here? He's like the DJ. Okay? He's like, oh, he's a big guy. I was like, And all the bosons, they're bringing booze to all the leptons. They're like, hey, keep going, guys. This is fun. That was the early universe. Okay. No structure, just complete mess of soup. And as the universe expanded, like that balloon, things got colder and colder and colder. It's like who has a bicycle pump? When you pump the bicycle pump, what happens? It gets hot. It was almost. Good one. Would you like to be in my class? I do this to my students all the time. Okay. I'm going to pull a few other ones, so be careful. So yeah, you put, or the back of the fridge, right? The back of the fridge actually takes heat from your food, right? And if you look at the back of the fridge, it's hot in the back of the fridge because you're compressing gas to then expand the gas, which takes in heat. Maybe a bit too much for this. But what's happening is as the universe is expanding, it's getting colder. Okay? And as things get colder, people kind of settle into little apartments. They don't talk to each other like the winter. Okay? In a lot of ways, it's like Montreal. You know, like I used to be, like when I was younger, it was like spring came around, you know, at first 10 degrees in March, and you had a girlfriend, you're like, see ya. And it's like, and then you know, October 31st came around, you got the winter, it's like a big dance of musical chairs, people trying to get together. That's, as things get cooler, more and more structure gets in place. And that's what we're living right now. We're living in a universe, and Einstein actually was right, is that we're living in a universe that's expanding and it's actually staying constant. It's not like going to crunch back onto itself, and things are just getting colder and colder and colder. Not fun. Round 2. Okay. Einstein. Everybody's favorite. Everybody likes this guy. Right? Okay. Everybody likes this guy. And this is why you can't really do, you know, and we're not going to talk about, Einstein didn't like formulate the ideas of black holes, but without Einstein, we couldn't even talk about black holes. And, you know, I have to mention this guy called Wheeler, who was the guy who was saying, hey, there's something called a black hole. Nobody thought he was crazy for 25 years until we proved they actually existed. But Einstein's work is what allowed us to even formulate the fact that there could be black holes. And I think that this movie, I never got to see this movie when I was a kid, and I threw a complete meltdown when I lived 40 minutes away from the cinema. But this was a Disney movie, and I think the tagline is really good. A journey that begins where everything ends. Right? And this is kind of like the way we structured this talk, because black holes really are the end of things, okay? And they are they're the infinitely small that determines how things, the infinitely large actually is held together and will end. So here we have Hubble hanging out, going, hey, I have this thing, it's called a telescope. Einstein goes, hey, I never ever like actually touch physical objects. All I do is like work on blackboards. And they're actually hanging out together. Right? And this is actually, those two guys, they didn't know it, but together they actually formulated pretty well the basis for the next 100 years of physics. So a little bit about Einstein. He actually won his Nobel Prize for stuff with electronics, the photoelectric effect, the fact that your solar calculator works, Einstein. Okay? He did a lot of other stuff besides what everybody knows him for, which is this, you know, just so everybody knows, theory of special relativity is where we do the E equals MC squared stuff. If you ever do a Creative Mornings on mass, you can give me a call. I can talk about mass. Okay. With the Higgs boson and all this stuff. But that's where the theory of special relativity. But what we're going to talk about today, and how much time do I have left?
I don't know.
Okay, so just screw the time. Screw it. Next, a time talk too, we could do that, but now we're just going to forget about time. So the theory of general relativity is what we're actually going to demonstrate. We have 10 minutes? Okay, thank you. Okay. Other things, you can't really do Einstein talks without quotes, right? So like this is like probably my favorite quote about Einstein. The most beautiful experience you can have is mysterious. It's a fundamental emotion which stands at the cradle of all true art and science. Okay? Creativity, not just in the arts. Actually, vast majority of artists I've met are more closed-minded than the scientists I've met. The key thing, and I think Andy Nolman and I see like this is the same way, is that I actually believe that unless, let's put it this way, when I was an astrophysicist, people used to go, God, I want to be an astrophysicist. I used to love to look at the stars. What did you do? And I go, well, I actually, you know, I'm all in my 20s. I don't remember those. I was in a lab. Like doing math. You were having fun. I was the guy inside doing the work. And so the thing with wanting to be creative is that being a real scientist, or I think being a real creative, is being on the limit of what the known and the unknown. Right here. And that's where things are confusing. And if you're not there, you're not pushing yourself hard enough. because that's where creativity happens. Your comfort zone, forget about it. If you want to stay in your comfort zone, you're going to be mediocre. And when I was an astrophysicist, people said, what's it like being an astrophysicist? And I went, well, actually, have you ever been to a country where there are no roads, where you don't have a GPS, you don't speak the language? You feel lost? That's how I felt every day. Every day you go to work, you go, so what are we looking at today? I have no idea. What did you see? I don't know, man. And the real difference between a scientist and a theologian is that a scientist is very, very comfortable saying, I don't know. Because that's where we are, on that cusp. And if you're not there in your life, you're taking it too easy. Yeah, come and work for my company. See, that's fun. This is my actual favorite quote from Einstein. Okay, and this is true. Who plays Civilization? There you go. This is a quote from Civ. Okay, a man who can drive safely while kissing a pretty girl is simply not giving the kiss the attention it deserves. Okay. Einstein was a huge humanist. He was also a total horn dog. You can look it up. Okay, it's just like divorced his first wife and whatever. So, let's talk about black holes. Okay, this is we'll start a little bit earlier than this. We'll stay at the quote, and now I'm going to ask for my volunteers with the fabric of time. So, good one. Eh? So, how does gravity work, right? The best way to explain this, to explain how space, and I'm not going to use the word space-time because that's another thing, but if you want to think about it, is that when there's no mass, space is flat. Kind of like this. You guys see this? Can we lower it down a bit? It's going to be hard on your back. Okay, lower it down. So you see space is flat. It's kind of like a grid. And if I have to shoot a light, let's just say you're on the other side of the galaxy, and I'm going, hi, and I'm shooting a laser will travel in a straight line. Because, a straight line is the shortest distance between 2 points, right? That's what we were taught in school.
Yep.
Yeah? So this is what gravity does to that concept. Boom. Any straight lines left on this grid? None. There are no straight lines. The universe is not simple, and yet still it's simple. So now when I shoot a laser, look at this. Over here it actually curves inside, like a saddle. See that? And here it curves down. Believe it or not, so we can stop this one for a little while. You guys can sit down. Thank you very much. Believe it or not, the sun does this. So what you think is flat space is actually curved. We are in the bottom of a bowl of space that's around the sun. And this is us. Okay? And what happens is that if you have linear momentum and you're caught in the gravitational field of the sun, we'll put the sun in the middle, you're going in a straight line, everything's fine. You're just a pile of dirt in space. And then the sun grabs you in the gravitational field. You're in a bowl. And this is what we're doing around the sun. Okay? And if there's friction, that's what we're going to happen. Luckily, there's no friction in space, so we're not going to spiral into like billion degrees of heat. So, but we are doomed nonetheless. So, that's literally what's happening here. Is that there's a bowl of space-time, and our linear momentum got caught in the gravitational field of the sun, and we're actually rotating like that in a bowl. And so are all the planets, and so are we around the supermassive black hole at the center of our galaxy. All that, it's all space being extremely deformed. Okay, are your minds blown? This still blows my mind. I've been doing it for 25 years. I'm like, God. So this is kind of like what people think a black hole would look like if we could actually see it optically, but we can't because light doesn't come out of a black hole. So it would bend space so much that it acts as a lens. Because that's what lenses do. They just bend light. So take that example here I had earlier. So I'll take my fabric of time back. Now. Yeah. And so what we do then is that we bend space so much, you guys can walk together. Okay, closer. Closer. No, I'm not going to make you kiss. Okay, so this is when people talk about the warp drive, if it ever happened. The warp drive would be this. This is what happens. Space-time is extremely bent, and then all you do is go, oh, look, we'll just go here, and then you unfold. That's how warp drive works, but it doesn't really work because it doesn't exist. But space, that's how black holes work, though, because what happens is that you're bringing it in, and then squish it all together in one tiny little thing. That's what a black hole does in time, in space. And now when I'm shooting my laser beam, it's going to go like this, and it's going to bend and turn on top of itself. So instead of just bending like this and going around the sun, it's actually going to bend so much, it'll make a circle. And the light will never come out. Because, black holes suck things in. You think, okay, it's just a heavy thing, that gravity. But light doesn't weigh anything. So if light has no mass, how can it get sucked in? Because it's not about sucking in. Black holes are not about sucking shit in. Okay? Black holes are about the curvature of space-time. Thank you very much, space-time people. Black holes are about really bending space so much that the light curves onto itself, and you just walk in a circle. So if I put you on the Earth and I go walk north, are you ever going to get off the Earth? You can walk as much as you want. If you stay on the surface of the Earth, you're just going to walk back right to me. That's what's happening inside a black hole. Okay? And the thing about black holes is that everybody thinks, oh God, they just get bigger and more massive and suck more shit in. It's called accretion. And everybody goes, oh my God, like there must be a white hole. No, no white hole. Deal with it. Deal with it. It's the end. And as stuff gets into a black hole, you become part of the black hole, and the black hole gets bigger. And that's it. The black hole at the center of a galaxy, sucking in stars, little planets like ours going poof out of existence daily. You don't even make it close to the black hole. And what's happening is that as you're being sucked into the black hole, well, I won't get into that. So, but the black holes get bigger and bigger, and the one in the center of a galaxy weighs 13.7 million times the mass of our sun. And it's about the size of the orbit of Jupiter. That big. There you go. And then how does this tie back to the infinitely small, right? Because my tagline is, the infinitely large is actually dominated by the infinitely small. So how do black holes start? Big debate. But one of the most accepted ways is by creation of a neutron star. So I'm going to explain to you how stars die. This is the end of the talk. Look, you guys, you're all sad. Oh. And so stars do die. We have about, I think, 2 billion years left on our star, but we'll die way before it's not going to explode, so bear in mind. But if the star is about 8 to 10 times heavier than our star, they actually do become something we call a type 2 supernova. And those are usually the things that start black holes. But they are also the things, death, again, we're getting into Tao of physics. You, me, all this stuff, everything that's heavier than lithium comes from an exploding star. Stars, and this is another talk, but stars are actually big element-making machines that are like onions. In the middle of that onion is iron. And this is going to blow your mind. Everything that's heavier than iron, lead, uranium, and all, is made in like the 8 to 10 seconds that the star explodes. Okay, you, me, mostly carbon, and a lot of hydrogen naturally was around the Big Bang, but like carbon, everything heavier than lithium. Aluminum, Rio Tinto, from an exploding star. Okay, silicon, most of the sand and the glass, exploding star. And what happens here is that in elements, stars have fusion, we'll explain it later on, but basically make heavier and heavier elements. In the middle of every star is an iron core, because iron is the last element that you can make where it gives off more energy than it takes in. So when you make iron, it becomes more expensive to make heavier elements than iron. So all the stars, it gets older, the iron core gets heavier and heavier and heavier, and it's extremely dense. But it's still this type of matter. Okay, protons don't want to get close together. And what happens is that these protons, kind of like in an office building, they're in their cubicles, my space, your space. We have this little electromagnetic charge, keeps us apart. So everybody takes up space. Because of the electromagnetic charge between the protons are just made up of these other quarks. Well, when gravity gets so strong, because it's actually gravity that's driving fusion in the stars, when gravity gets so strong, it does a sex change on all the protons. It's kind of like, yeah, that charge is gone. Gravity just wins. And all the protons become neutrons. Guess what? You don't have this problem of repulsion anymore. So all the neutrons, it's like you take like the CGI building full of like poor people working in cubicles, and you squish them poof, down to the first floor. And you're back to the party situation if you want. Right? That's what's happening in a supernova. Okay? And so the iron core of the sun, bang, implodes into the densest matter known to mankind, neutron matter. And then what happens? Well, you have all these other layers of the sun. Well, what do they see? They see empty space, and they just fall towards a hard core. Bang, this is hardcore. They hit the hard dash core, and they bounce off that core, and as the inner layers bounce off, boom, that's what causes the explosion of the star. All the other layers are then exploded, making cosmic dust that makes planets, that makes babies, that makes us. Okay, the nice poetic thing here about all this death is that death and rebirth. We are all made up of stardust. Okay? Back to death. So the sun, which is about, it's very, very big. It's millions of kilometers across. This matter becomes so dense that the entire matter of the sun would basically squish down to the island of Montreal of neutron matter. Okay, and now I'm trying to make this, Gabriel said, Claude, make it more so that people understand. So this, if we take the Earth and we convert it to neutron matter, how big would it be? Want to venture a guess again? The room. Anybody else want to venture a guess? You. That's pretty big. No, it would be a teaspoon. Okay, if you're eating neutron cereal, it weighs as much as the entire fucking planet Earth. That's nutritious. You got it. Pretty high calorie count too. So that's how dense. That's the kind of density you need to start a black hole. Neutron stars don't all cause black holes, but this is one of the things. And one of the other things that the quantum mechanics people say is that in the early soup thing that I did earlier in the universe, the galaxies today, this is, again, it's going to blow your mind, but galaxies, when normal astronomers who are Einstein fans are doing math, they go, problem here. Galaxies don't form fast enough for the age of the universe, and so we can't explain this. And then they turn to the quantum mechanics guys, who are us, you're an idiot. We go, obviously, they take into account the fact that in the quantum soup, there were random variations, because in quantum mechanics, everything's random, that made there were slightly denser areas in the soup. And those became what we call proto-black holes, and the universe expanded. So the formation of galaxies, the biggest thing we know, is actually determined by like tiny variations in quantum mechanics in the early universe. Infinitely big, actually determined by the infinitely small. And just so you know, I've never taken a stats course in my life, and I've never taken an astronomy course in my life. All I did was quantum mechanics, and then basically what the astronomy people, they ran out. They literally turned to us, and were like, "Hey, quantum mechanics guys, could you give us a hand?" And we're like, "You've been ignoring us for like 40 years." So this is where one of the reasons I actually became an astronomer. Anybody here remember the superconducting super collider that was canceled by Clinton. Clinton said it was his, over the war in Serbia, Clinton said it was his biggest blunder to cancel this, because we spent $5 billion to build the hole, and then we spent $7 billion to fill it up, and we could have built the whole thing for another $2 billion, so it doesn't matter. But a whole bunch of people in my field were like, oh, shit, I was planning my life around this superconducting supercollider. What do I do now? Well, black holes. They're very big accelerators, okay? Everything around the black hole, if it's not falling in, is going to very high energy, like nothing like we can build on Earth. So what I did is I helped pioneer a new form of astronomy that actually looked at the world through particle physics lens. It's like the ultimate victory of quantum mechanics over gravitational and Einsteinian forces. So my area of specialty was blazars, and blazars are just a form. All galaxies now, thanks to us, we think have a supermassive black hole in the middle. And depending on which angle we see the galaxy, if we see it on the edge, we'll see what we call a radio galaxy. If we see it on the edge, we turn it towards this way. So here's the axis of the middle of the galaxy, right? And the galaxy's flat. If we see it this way, we'll see what we call a quasar, which people used to think were quasi-stars. That's why they gave them that name. As opposed to our baby, will be half Australian, half Quebecois. We're calling him a quasi. Quasar, quasi. And so then you get into what we call X-rays. And as you go up in terms of how much a galaxy is facing you, you see a higher and higher energy emissions. And I was actually looking at the super, super high energy emissions that come when galaxies are facing straight us. And so we're ending now on this slide. How much time do we have left? Minus 2 minutes is great. Perfect time. This is actually what we call the Hubble Deep Field. Who's seen this? Okay. This is probably one of the most expensive photos ever taken in the history of humanity. Right? We just left the Hubble telescope on. Just go look. Take in as much light as you possibly can. There's billions of galaxies. Billions. We can't even count them. Every one of those galaxies, we think, has a supermassive black hole in the middle of it. Every one of those. And it's all thanks to that thinking, the fact that we can even talk about this today is thanks to two guys. Thank you very much.